Hello, I'm Chi from the University of Chicago. Today, I'm going to talk about statically inferring performance properties of software configurations. This is a joint work by Wang, Professor Hoffmann, and Professor Shan.
Modern software often has hundreds of configurations. The number of software configurations increases dramatically over the years. Do users know how to use these hundreds or thousands of configurations? The answer is no. There are many forum posts like this one who ask which configuration can be tuned to improve performance. Even when the user knows which configuration to tune, they still often struggle at figuring out how to tweak a configuration to achieve certain performance goal. Consequently, it's not a surprise that performance-related misconfigurations are very common and they lead to severe incidents. Previous study has found that as many as 65% configuration issue report and 35% configuration questions on Stack Overflow are related to performance. Furthermore, about 20% to one-third of these performance misconfigurations are very severe, causing severe slowdown or out-of-memory errors. So, can we help? Particularly, can we develop a technique that can automatically answer the questions like, does this configuration affect performance, or how does this configuration affect performance? Previous attempts to solve this problem used machine learning or control theory-based approaches to learn the relationship between performance and the configuration through offline training. Although promising, these techniques relies heavily on training and profiling. They take a lot of time and only work when runtime workload and the environment is similar to that during the profiling time. So, can we do better? Our key observation is that software dynamic behavior, including performance behavior, must reflect its static programming logic. Therefore, we can potentially use static programming analysis to infer runtime performance information. Particularly, to answer whether a configuration affects performance, we can check whether there exists any static program dependency between this configuration and any expensive performance operation, short for perf-op. If the answer is yes, to know how this configuration affects performance, we can further analyze what type of program dependency is there. Let me show you a simple example. IO.MB is a configuration in MapReduce. Does it affect performance? Without doing any profiling, we can just look at the source code. As you can see, its value is stored in the sort.mb variable, which is then used to compute the integer called max usage, which is then used as a parameter of a memory allocation operation. So we can conclude that IO.MB can affect memory consumption at runtime, and its impact is a positive linear relationship, not a single experiment needed. Based on this insight, our key idea is to use static program analysis to figure out which configuration and how the configuration affect performance. Actually, there's already well-known dependency taxonomy in program analysis. It could either be data dependency or control dependency. We found that with a little bit more analysis about static dependency, then we can indeed infer how configuration affect performance. As you can see, different types of static dependency between performance operation and performance configuration can map to different runtime configuration performance curve. Following the taxonomy, we build a static analysis tool, LearnConf, which takes system binary as input and output performance properties of configurations. It automatically identifies performance-sensitive configuration like this IO.MB, whose setting can affect execution of a long latency or large memory operation like this new byte through dependency analysis. LearnConf also analyzed the exact dependency pattern to figure out more detailed properties of a configuration. Like this, IO.MB affect memory consumption of every map task in a monotonic, linear way, with the linear slope being 1024 times 1024, and so on. We evaluated LearnConf on four widely used distributed systems: MapReduce, HDFS, HBase, and Cassandra. Each of them contains 100 to 150 configurations. Our evaluation shows that LearnConf can correctly identify 60 out of 71 true perf-confs with only 9 false positives. Furthermore, LearnConf can even find 4 configurations that are not mentioned in performance tuning tutorial and papers that can actually affect performance, causing out-of-memory or timeout failures. We also confirmed the inferred performance configuration relationship using experiments. Thanks. Any questions welcomed.